So in 5.2, we are looking at a very special type of probability distribution. We're looking at a binomial situation. So here are the conditions for a binomial experiment. Number one, there are only two outcomes. So flipping a coin is a classic example of a binomial experiment. It's either heads or it's tails. Another way that we can define this is by success or failure. Either yes, the event happened, or no, it did not happen. Either you got it wrong or you got it right. Okay, that would be a binomial situation. The probability of success is identified with the variable p, and the probability of failure is identified with the variable q. And if you add these two together, they equal 1. So they're complements of each other. Again, we talked about this earlier. If there's a 70% chance of rain, there's a 30% chance of it not raining. That's the idea of a complement. So in a binomial experiment, you have two events, the probability of success and the probability of failure, okay, which are complements of each other. There is a fixed number of trials. You run an experiment 5 times, or you flip a coin 13 times. There is a fixed number of trials that you do. And then finally, each of these trials are independent, which means the results of the first trial do not impact the second trial, and the results of the second trial do not impact the third trial. Each trial is completely independent. So these are important ideas, and we know what independent means, right? We've talked about in the last chapter, situations, trials being dependent and independent, probabilities changing. And because the trials are independent, P and Q do not change from one trial to the next. We're going to derive the formula for calculating probabilities with an example. So in this situation, we have 3 trials. Question number 1, question number 2, question number 3. Okay, so there's 3 trials. And for each trial, you have 4 answers, 3 of which are incorrect and 1 that is correct. So this is your standard 4-question multiple choice test, right? So what is the probability of getting the question correct? 1 out of 4. What's the probability of getting the question incorrect? Now, you could use the idea of a complement, or in this situation, it's easy to just count them, 3 out of 4. So we have 3 trials. The probability of each trial being correct is 1 out of 4. The probability of each trial being incorrect is 3 out of 4. So is this a binomial experiment? Does it meet all of the conditions? So the questions are either correct or incorrect. So there's only 2 outcomes. Check. What are the values of P and Q? So like we talked about, P is 1/4, 1 out of 4, or 25%, and Q is 3 out of 4, or 75%. Are there a fixed number of trials? Yep, there's only 3 trials because we have 3 questions. And are the questions independent? If you get question number 1 wrong, does that mean you're going to get question number 2 wrong, or does it change the probability of question number 2? And we're going to say no, they're completely independent. We have a binomial experiment. Now the big question, what is the probability of getting exactly 2 questions correct? So what are all the possibilities you can have with these 3 questions? Well, you could get all 3 correct. That would be one possibility. Or you could get the first 2 correct and the last one wrong. You could get the first and third one correct and the middle one wrong. Or you could get the first one wrong and the last 2 correct. In each case, these are all 2 correct answers. And now let's look at the other options. You could get the first one right, only the first one right. You could get only the middle one right, or you could get only the last one right. And again, these are situations where you get exactly 1 question correct. And then you could get none of them right. In this sample space, what are the events that meet our criteria of getting exactly 2 correct? Well, that would be these. So this is our event space. What is the probability of this event space happening? So let's find the probability of just one event, just this one single event. If we can find the probability of this one, that's going to be the same as the probability of these other two. So consider this. What's the probability of getting the first one right, the second one right, and the third one wrong? So since they're independent, we could just write it like this. The probability of getting the first one right is 1 out of 4, right? That's P. What's the probability of getting the second question right? 1 out of 4. What's the probability of getting the third question wrong? 3 out of 4. And if you were clever, you could write this as 1/4 to the second power, 3/4 to the first power, or P to the second power, Q to the first power. So this is the probability of that situation. It is also the probability of these other two situations. So if we wanted to find the probability of the event space, it's going to be 1 out of 4 to the second power times 3 out of 4 to the first power times 3 because there's 3 of them in this space. So maybe you noticed a pattern, and there is a pattern going on here. There is a formula hidden behind the scene here. And maybe in order to flush out that formula, we need to look at all of the examples. What is the probability of getting all 3 right? What's the probability of getting 2 right? What's the probability of getting 1 right? What's the probability of getting none of them right? And that's what we do here in this table. So the probability of getting 0 correct is 1/4 to the 0 power, 3/4 to the third power. The probability of getting 1 correct is 1/4 to the first and 3/4 to the second. Now, this can happen 3 ways. And so you multiply it by 3. What's the probability of getting exactly 2 correct? This is what we just found out, right? This is the problem that we just did right here. So it's 1/4 to the second power, 3/4 to the first power. And how many ways does that happen? 3 ways. So we multiply by 3. Finally, what's the probability of getting all 3 correct? 1/4 to the third power, 3/4 to the 0 power. And there's only one way that can happen. Do you notice a pattern with the exponents? What do you notice about 0 and 3, 1 and 2, 2 and 1, 3 and 0? If you add them up, they always equal 3. How many trials do we have? 3 trials. There are 3 trials, and our exponents always add up to 3. If you look at P, the probability of success, that is to the power of the number of successes. And the power of failures is the total number minus the number of successes. So look at this. In this example here, we got 3 correct, right? All 3 are correct. So that is the number of successes to the third power, the number of failures to the 0 power. How many did you get correct? 3. How many did you get wrong? 0. P to the third, Q to the 0. Look at this other example where we had 2 correct. P to the second power. How many did you get wrong? 1 wrong. If I got 2 correct, that means I got 1 wrong. So P to the second power, Q to the third power. In general, here is the formula. So for a binomial distribution, you can calculate the probability of an event by taking P, raising it to the number of successes, times Q, raised to the power of the number of failures. And then there's this guy, the counter out front. Do you recognize that? NCR? This is the formula for a combination. Combination pizza where order doesn't matter. this guy kind of pops up, and we're actually going to explain why that pops up next time.